World Spaceflight News Special Report. Welcome to this WSN preview of the fascinating LOFTID mission. NASA, led by Langley Research Center in partnership with United Launch Alliance, will conduct a flight test of an inflatable aerodynamic decelerator technology to demonstrate its performance in environments relevant to several mission infusion opportunities. The Low Earth Orbit Flight Test of Inflatable Decelerator, LOFTID, Reentry Vehicle, RV, will be flown as a secondary payload on an Atlas-V launch vehicle. After the primary payload is delivered to the desired Earth orbit, the Atlas-V Centaur upper stage will deorbit the LOFTID RV. Prior to atmospheric entry, the RV will inflate the aeroshell, and then the Centaur will orient, spin up, and release the RV for its spin-stabilized ballistic re-entry. The flight will demonstrate the high-mass entry, descent, and landing technology at a scale, 6-meter, and atmospheric conditions similar to landing large payloads on Mars as well as return from Earth orbit. This capability could also enable applications such as launch vehicle flight hardware recovery and reuse and return of products manufactured in space for terrestrial use. Conducting this effort with an industry cost-sharing partnership allows NASA to significantly reduce the overall cost of developing this technology while enabling a potential commercial user to gain insight into utilizing this technology for future booster recovery. NASA and United Launch Alliance, ULA, announced in September 2021 that they would dedicate the launch of the LOFTID mission in honor of Bernard Cutter, ULA's Manager of Advanced Programs. Cutter passed away from a sudden heart attack at the age of 55 in August 2020. He was not only an advocate for more lower-cost access to space, but also the technologies that could make it a reality. The ULA engineer took a keen interest in NASA's inflatable heat shield technology, which could enable the safe return of Vulcan rocket engines as part of ULA's reuse program, as well as land large payloads on Mars required for crewed missions. To get LOFTID to fit into the rocket, it will be packed inside the JPSS-2 payload adapter. The payload adapter is the structure used to connect JPSS-2 to the rocket. After JPSS-2 separates from the Atlas-V, the payload adapter must be separated from the launch vehicle before LOFTID can start its demonstration mission. After it separates, it will demonstrate how the inflatable aeroshell, or heat shield, can slow down and survive re-entry through Earth's atmosphere. This is a unique flight configuration, said Sean Hancock, LOFTID payload adapter lead and aerospace engineer at NASA's Langley Research Center in Hampton, Virginia. Because of that, we developed a LOFTID-specific separation system. The LOFTID Payload Adapter Separation System, PASS, uses a series of springs, which release and initiate separation of the payload adapter from the launch vehicle. Then, like a reverse slingshot, the springs mounted to the payload adapter retract, pulling a net against the LOFTID re-entry vehicle, shooting the LOFTID payload adapter away from the re-entry vehicle. That system was recently ground-tested at NASA Langley. Because actual separation will take place in zero gravity, testing on Earth requires some specialized hardware to simulate a space-like environment. The team used a flat floor with air bearings, like an air hockey table, which allows anything parallel to the floor to be near frictionless, imitating zero gravity in that direction. A mock-up of the LOFTID re-entry vehicle was attached to a wall, and a model of the payload adapter separated from LOFTID and glided on the floor using air bearings to test how well the system works. The tests used an engineering development unit and were successful. NASA's Bernard Cutter Low Earth Orbit Flight Test of an Inflatable Decelerator, or LOFTID, is demonstrating a cross-cutting aeroshell, a type of heat shield for atmospheric re-entry. For destinations with an atmosphere, one of the challenges NASA faces is how to deliver heavy payloads, experiments, equipment, and people, because current rigid aeroshells are constrained by a rocket's shroud size. One answer is an inflatable aeroshell that can be deployed to a scale much larger than the shroud. This technology enables a variety of proposed NASA missions to destinations such as Mars, Venus, Titan, as well as return to Earth. When a spacecraft enters an atmosphere, aerodynamic forces act upon it. Specifically, aerodynamic drag helps to slow it down, converting its kinetic energy into heat. Utilizing atmospheric drag is the most mass-efficient method to slow down a spacecraft. The atmosphere of Mars is much less dense than that of Earth and provides an extreme challenge for aerodynamic deceleration. The atmosphere is thick enough to provide some drag, but too thin to decelerate the spacecraft as quickly as it would in Earth's atmosphere. LOFTID's large deployable aeroshell and inflatable structure protected by a flexible heat shield acts as a giant brake as it traverses the Martian atmosphere. The large aeroshell creates more drag than a traditional, smaller rigid aeroshell. It begins slowing down in the upper reaches of the atmosphere, allowing the spacecraft to decelerate sooner, at higher altitude, while experiencing less intense heating. LOFTID is demonstrating a large aeroshell 6 meters in diameter or about 20 feet entry from low Earth orbit, to demonstrate this technology in conditions relevant to many potential applications. The benefits of using the inflatable decelerator design for a variety of space applications include low Earth orbit return, free flyer, in-space manufactured materials, 3 to 6 meter scale. International Space Station down mass greater than currently possible, 8 to 12 meter scale. Lower cost access to space through launch vehicle asset recovery, 12 meter scale. The LOFTID re-entry vehicle is scheduled to launch no earlier than November 1, 2022 aboard a United Launch Alliance Atlas V as a secondary payload with the Joint Polar Surveyor System 2, JPSS-2, a polar orbiting weather satellite. After JPSS-2 reaches orbit, LOFTID will be put on a re-entry trajectory from low Earth orbit to demonstrate the inflatable aeroshell or heat shield's ability to slow down and survive re-entry.
If you ask anyone who has ever been involved with the Mars mission, they will tell you that successfully landing on or orbiting Mars is incredibly difficult. In fact, of the more than 40 missions that humans have previously sent to Mars, less than half have been successful. One of the major challenges that face NASA researchers is how to deliver heavy equipment and people safely to the surface of Mars. Popular movies and science fiction articles make landing on a planet look easy, but in fact, that is one of the hardest elements to achieve. There are a host of aerodynamic and physics issues that engineers need to overcome. First and foremost is decelerating a spacecraft, traveling many times faster than a bullet, and allow it to gently land with precision onto another planetary surface hundreds of millions of miles away. To date, the maximum weight we have landed on Mars is about 1 ton, but when humans arrive, we'll need to land 15 to 20 tons onto the surface. The only way to accomplish this feat is to innovate and come up with a new strategy. a small group of dedicated NASA engineers, researchers, designers, and craftspeople are currently working on making a safe entry into the Mars atmosphere possible. The technology is called HIAD, for Hypersonic Inflatable Aerodynamic Decelerator, and it promises to redefine how we deliver spacecraft to Mars and other planets with atmospheres. Coming up on this episode of NASA X, we will take a look at the difficulties associated with landing on a planet like Mars and see how the NASA HIAD team plans to overcome the tremendous challenges faced with landing there. We will also visit the labs and partner companies who are helping to build HIAD and see firsthand what true innovation looks like. Entry, Descent, and Landing, or EDL, is one of the most challenging aspects of any lander mission. That's because landing a spacecraft is hard. Whether you are landing it back here on Earth or on another planet like Mars. Although it's not easy on either planet, Earth's atmosphere does offer more help to slow down a speeding spacecraft. This is because our atmosphere is dense compared to Mars. When a spacecraft flies through an atmosphere, aerodynamic forces act upon it to help slow it down. The drag that is created on the craft allows it to decelerate to the point where subsonic parachutes can be deployed, or in the case of the shuttle, where a guided landing could occur. The same can't be said for a Mars landing. The Martian atmosphere is very thin and much different than Earth's. In fact, the densest portion of the Martian atmosphere is only about as thick as our atmosphere is at 100,000 feet. As a result, a spacecraft flying through the Martian atmosphere does not generate as much drag, so it cannot be slowed down as quickly as it could back on Earth. For most laypeople, two immediate thoughts may come to mind about how to slow a craft at Mars. The first is to use rocket propulsion. In theory, this is a good plan, but in actuality, the amount of fuel needed would be enormous. One NASA study determined that landing 40 tons on the surface of Mars would require over 60 tons of rocket fuel. The other thought is to use giant parachutes. However, this much mass would require a cluster of parachutes, each the size of a football field, to be deployed while traveling more than 2 times the speed of sound. So to the HIAD team working on this problem, the solution is clear. Use a larger vehicle so that the Martian atmosphere slows us down higher up in the atmosphere. Previous missions have used the atmosphere to successfully slow a craft, but the mass and entry speed of these spacecraft, coupled with the thin atmosphere, limited landing areas to only the lowest elevations on the planet. In fact, currently only 40% of the Martian surface is accessible for 1-ton payloads. Clearly, these are major issues that must be overcome before we can send larger payloads and eventually humans to Mars. So how do we overcome all these obstacles? Here at NASA, a group of engineers and researchers are working on that exact problem, and they have come up with a solution that looks like the most viable option available to us. They call it HIAD, or Hypersonic Inflatable Aerodynamic Decelerator. Here is Dr. Neil Cheatwood to explain.
If you look at how we get to Mars now, we're using the technologies that we developed back in the 60s and 70s for Project Viking. That was the first time we successfully landed on Mars. Way back when, in the 60s and 70s, Project Viking had a technology development effort, and that's where they developed a thermal protection system that was known as SLA, Super Lightweight Ablator 561V for Viking. And we've been using that for every successful mission to Mars up until our most recent venture, the Curiosity rover. So we had that TPS that was heritage from way back when. The disc gap band parachute, the supersonic parachute, was developed under the Viking program. And we're still using all these things. We're still flying the same aeroshell four-body shape that we had from Project Viking. So we've been living off of that heritage, off of that legacy. But with the Curiosity rover, we basically landed as much mass as we possibly can at Mars, at least at that altitude. If we tried to land more, we would end up hitting the surface before we achieved all the sequence of events that we had to achieve in the timeline. If we wanted to land that same rover at a higher altitude, also we would run out of time. We would hit the ground before we finished everything we needed to do. And so that was our motivation when we started looking at Irby, the first Irby mission. And so what we had done, one of the guys that was involved in this had done some research and seen a concept that the Russians were developing. And they tried flying this inflatable aeroshell, something where you could deploy something bigger, and a larger drag device lets you slow down faster, so you can either land that same mass at a higher altitude, it just natural falls out of the equations, or you could bring in more mass and land it at the same location. So we were looking at deployable devices. The Russians were looking at this inflatable aeroshell, but they covered theirs with an ablative thermal protection system, and we were concerned that maybe that wasn't the way to go. And so we started looking at one where we could just make it bigger so that we could keep the heat rate down lower and not use an ablator. But with the human scale, now you want to land 40 metric tons, or certainly at least 20 metric tons. And it's like, holy cow, how are you going to do that? Let's talk some numbers. With the Curiosity rover, that mission, the Mars Science Laboratory, is the largest aeroshell we've ever built. So the aeroshell is what protects us when we go through the atmosphere. It's a cocoon for our payload, for our science. So that structure, that protects that, and to protect the structure, we have to have that heat shield that protects us. That aeroshell for MSL, Mars Science Laboratory, is a little over 4.5 meters in diameter. Biggest one we've ever built. It's bigger than Apollo, bigger than anything. It's a big aeroshell. Even with that large aeroshell, what it contains within that rover and all the experiments are so heavy that we can't decelerate fast enough to reach the higher altitudes of Mars. In fact, the best we can do with that system, we can't even get to what was the Mars sea level. So we're landing below what was the Martian sea level. Where it ultimately landed is about -1 kilometer, so a kilometer below that sea level location, because it's just so heavy. If we had a larger aeroshell, then we could decelerate that mass sooner.
That larger aeroshell could be a HIAD. Because the launch vehicle can only physically accommodate a certain size payload to fit inside the fairing, engineers believe that an inflatable aeroshell is the best answer to get larger mass items onto other planetary surfaces with atmospheres. The basic concept of a HIAD is pretty simple. The payload is placed in the center, surrounded by a group of rings, or tori, that look very similar to large inner tubes. The tori are stacked in such a way that different diameters will be stacked one on top of each other and strapped together. Then, a flexible thermal protection system is placed around them to create a more smooth and heat-resistant surface. The materials used are incredibly strong fabrics like Xylon and Kevlar, but can also easily fold into the rocket shroud. Once inflated, these craft can become stronger than steel and handle tremendous loads.
Well, one thing that maybe can give people an idea of how structurally strong and durable these inflatables are is that a 15-meter design of an inflatable aeroshell is designed to take a load of about 300,000 pounds during entry. So 300,000 pounds is approximately 100 cars. So if you think of stacking 100 vehicles on top of this fabric structure is very impressive. That structure this made out of cloth and woven materials can take that kind of load.
Once the craft arrives at its destination, the HIAD will inflate to enter the atmosphere. all of these strong heat-resistant materials will act together to keep the payload safe from heating, while slowing the craft down long enough to land at virtually any location. This device has already undergone spaceflight tests and has proven to be incredibly successful. It has been flight tested twice, most recently on a test called IRVI-3. IRVI-3 launched in 2012 from the NASA Wallops Flight Facility on Virginia's eastern shore. Although it was a relatively small test, the data that it produced gave the team the confidence they needed to continue exploring this concept. IRVI-3 entered Earth's atmosphere at Mach 10, 10 times the speed of sound, and successfully survived the heat and forces of the journey. Temperature readings recorded on this suborbital test were as much as 1,000 degrees Fahrenheit, and the device experienced forces up to 20 Gs. This test opened the doors to larger missions and the opportunity to construct larger HIADs. Up next, we'll see how a new HIAD article is custom-made by hand in a unique facility in California. When you think about building a craft to travel to other planets, you may think about men and women in pristine buildings coming up with designs and concepts on the computer, then high-tech machines and tools used to help put them together. In truth, that is how many craft are built, but in these early stages of HIAD testing, the places where these devices are being constructed look more like workshops than pristine clean rooms. And although the men and women working on this concept are using computers to aid in their development, there are also skilled craftspeople that are putting together these devices just like a fine tailor may put together a suit. Here in this nondescript building in California, you can see how these fabric pieces are put together.
They're tailored. It's an art form. I mean, you can't just plug it into a computer and spit it out and make this. There's a hands-on, huge hands-on influence, and that's mostly where my side comes in, communication with how to build these things, figure out how to get the finished product we want from materials we've never worked with before in our lives. There's the major components to the torus. We have the braid, which is the outer material you see with the crisscross. We have the liner, which is inside of that, which is the seal. It basically keeps the air from leaking out. And then we have an adhesive we use for coating and for bonding all the pieces together. On the table, everything's laid out flat, so it's not in this curved shape when we're building it. It's straight in a tube. We take all our measurements straight. We use squares and basic tape measures, rulers, mark with a permanent marker and make a cut. With the ends, it's like the end of a t-shirt. If you cut it, the ends will fray. We have to kind of doctor the ends up to make sure that they don't fray and unravel, so we can consistently have the length we wanted. These liners can be 200 feet long, and there's a line that I've drawn that I have to keep, and I just walk along and cut this line, but because there's no machine that's out there to make a cut that long. So and at this stage it's all handwork, so we basically piece it together, and if the piece isn't wide enough, like the liner inside the torus consists of 3 different pieces. It's got, because the material is not wide enough to go all the way around, we have to put seams together to get the size we want. So I have to not only cut the panels and line them up, then I have to butt them up and then glue the panels together with an RTV adhesive we use. The yellow and red one are both the same construction. The yellow one hasn't been coated yet, so it's built to the right shape, but all the pieces haven't been tied together.
When the braid's finished like this is uncoated, so if you take the pressure out of this article right now, the braid will get completely disorganized, and the gas barrier inside the braid would actually become disassociated with the outer layer, so when you went to inflate it again, the barrier would probably wrinkle up inside, and you'd have localized elongation that would exceed the capabilities of the material, and you'd probably spring leaks in it. And also the braid itself would tend to open up gaps. So before we can deflate it, we have to coat it, and we use this high temperature silicone coating. It's a RTV that we put on it. It helps organize the braid, And it also, we push it through the material so that it adheres to the gas barrier on the inside, so those stay locked together in a matrix.
After putting together these tori, the next step is to begin testing. Up next, the article is placed inside a hydro rig while engineers test the HIAD's ability to withstand high pressure.
Yesterday we were performing a test to prove that the article can take a certain amount of pressure inside of it. I have to work around this thing. As the pressure gets increased in them, with air inside of it, if it pops, it's like a balloon. You pop a balloon, and even though it doesn't have much pressure in it, you pop it makes a loud noise. There's this energy going somewhere. If you take a water balloon and put it underwater and pop it, the only thing you're going to see is you're going to see the outside of the balloon just kind of disappear. You're not going to have any of this effect or movement. So what we were doing is we were testing the article to a high pressure that we calculated would be good to, but we don't want to test it with air, because if it did pop or rupture or have a failure, then it would be like a balloon on steroids. So by putting it underwater, filling it with water, taking it to a pressure which is higher than we would ever operate it at, we have that cushion and that comfort level. I can stand next to it and know that it's safe to operate and be around.
So as lead for the inflatable structures development, I'm working with a group of engineers. We're doing analysis work to structurally analyze the design to make sure it can take the loads that are being applied. We have to also look at the thermal properties of the material so it can withstand the heating environment. And we're also doing a lot of material testing. So everything from testing from the strength of materials to being able to withstand the temperatures.
The team has good data about these smaller tori, but if we are to use this concept to eventually land humans on Mars, we must get these sizes much larger.
One thing about soft goods is they're hard to characterize. We have a lot of analytical models that we have pretty good faith in now that we've developed over the course of the HIAD project. But still, as we make these large jumps, there's not a lot of faith in them. And so the only real way to get data is to build these things and test them.
The tori stack that is being manufactured here in California is the structure, the interior piece of the HIAD. But the flexible heat shield, the external piece, is being designed and built across the country in Dover, New Hampshire. At this facility, a small team is developing the process that will be used to sew together the cutting-edge materials used on the exterior of the HIAD structure. Because the external shielding will see the highest temperatures, it must be made from materials that can withstand the massive heating environment the HIAD will encounter.
Flexible thermal protection system is part of a re-entry system that could be used to bring things back from the space station or ultimately go out and provide larger payloads out to Mars. It incorporates a thermal protection system outer layer with an inflatable interior portion which provides the shape and stability. The fabric is silicon carbide, which allows it to take the high heat loads, unlike other materials that we've tried past. The insulating layers are carbon felts and an aerogel material. They're backed up by a gas barrier, which prevents any gases flowing through the entire system. So the highest temperature rated materials on the outside, and then insulators to prevent the gas barrier from overtemping.
Although this material is incredibly resistant to heating, it is somewhat challenging to manipulate in the construction process. That difficulty has forced this team to come up with innovative proprietary sewing and manufacturing procedures to outfit the HIAD. Once the outer shell is married with the internal structure, you have a very strong, heat-resistant cover that can be folded and packed to fit within a rocket shroud. And the combination of all the parts together now make flying to Mars and other planets with atmospheres much more viable.
This technology is not just an incremental advancement in our entry capabilities for NASA. This is actually a leap. We're actually making a big change in what our capabilities are. It's a new way of doing business. Actually being able to have very large entry vehicles changes the way that these payloads come into the atmosphere. We're looking at actually using HIADS, the inflatable decelerator technology, to recover launch assets, both first stage recovery as well as second stage. So that we're not really talking about these vehicles being the same shape that you would have coming into an atmosphere where you're delivering a payload, but actually maybe something a little bit elongated that conforms well to the launch asset that you want to recover, that gives it more of a gliding reentry or a gliding capability back to Earth.
Whether it's a fair expectation or not, those of us in the public have come to expect NASA and its partners to always come through with solutions to overcome challenges. The brilliant team working on HIAD has done just that. The ideas and processes they have developed have pushed through some big barriers and will almost certainly help us land on far-off places like Mars, while also being used back here in our own atmosphere on Earth. It just goes to show that virtually any technological issue can be overcome when you put the right team of people on the problem. And this is truly the right team.
As Sarah mentioned, I'm Joe Del Corso. I am the LOFTID project manager. I've actually been working this technology since 2005, since the original payday effort. I'm going to be basically just walking you through some of the technology development history, how we got to where we are, why this technology is important, and then and then I'm going to hand it off to my colleague John Donato, who is our chief engineer on LOFTID, and he's going to go through some of the details down and in on the hardware. So HIAD is the hypersonic inflatable aerodynamic decelerator technology. That's what we are demonstrating on LOFTID. The original concept actually comes from the 50s and 60s. Unfortunately, during that time, they did not have the materials or structures. They were not sufficiently advanced enough to actually realize the capability. More recently, one of my colleagues, Steve Hughes, a world-class engineer, picked up the technology around 2003, recommended it to NASA, and with the assistance of PI Neil Cheatwood, we were able to start garnering some funding for the technology. So in 2005, we started our first ground development effort called Payday, the project to advance inflatable decelerators for atmospheric entry. It is a mouthful, I admit. During that ground development effort, it was really very rudimentary, testing proof of concept, whether materials can withstand hypersonic flight regimes. From there, we had a flight test in 2007 called IRVI, the Inflatable Reentry Vehicle Experiment. Unfortunately, due to a launch vehicle anomaly, there was no experiment. So we then were able to fly IRVI-2, the Inflatable Reentry Vehicle Experiment number 2 in 2009, which was an IRVI build to print. We launched out of Wallops. That was a 3-meter scale aeroshell. The sounding rocket that we launched on was the smallest in the Wallops arsenal. And basically it went straight up and came straight back down. So it was a good proof of concept and it worked beautifully, but it wasn't sufficiently mature at that point to do an orbital entry. At that point, we were simply looking at whether the concept works. Because of the success of IRVI-2, NASA invested in a ground development effort, which has become the nomenclature for the technology called the HIAD ground development effort, the Hypersonic Inflatable Aerodynamic Decelerator ground development effort. That was in 2009. During that ground development effort, we essentially matured material systems, manufacturing processes. We matured our entire infrastructure, how we deal with flexible systems as a whole and flexible aeroshell. From the success of HIAD, the first ground development effort, we then went into a flight test called IRV-3. During that flight test, we launched again out of Wallops on the largest sounding rocket in their arsenal. Again, went straight up, came straight back down, but this time we had much more advanced inflatable structure, more advanced flexible thermal protection system, higher heating, and we were able to show controllability during entry. From there, we went to another ground development effort called HIAD-2, which lasted up until our LOFTID flight test. During the HIAD-2 ground development effort, we focused instead of just concept and demonstration, we focused on increasing scalability of the aeroshell. We went from 3-meter scales to 6 meters to 12 we looked at going up to 18-meter scale and 20-meter scale with these aeroshell. Now, in 2018, STMD, as Trudy mentioned, started off LOFTID, the low Earth orbit flight test of an inflatable decelerator flight project. This is a demonstration of the HIAD technology at a 6-meter scale and at environments that are relevant now to Mars and human missions. Let's go to the next slide, please. So why is HIAD important? What's the purpose of HIAD? HIAD is a deployable aeroshell. It can be packed and stowed into small volumes for launch and for the cruise phase of a mission. We can then deploy it exoatmospherically or in orbit in order to decelerate heavy payloads and put them onto the surface of any destination with an atmosphere. Why does this matter? Currently, using rigid technologies, using rigid aeroshell, we're limiting the size of the aeroshell itself to fit within the fairing of a launch vehicle. That means that we are limited to about 4.5, 5-meter aeroshell sizes. What does that mean? That means that the larger the aeroshell, the more down mass capability you can put to the surface of a planet. So if you're limited to 4.5, 5 meters, that limits you to about 1.5 metric tons of down mass capability. Using the HIAD technology, we are looking to expand that to 20 to 40 metric tons. The equivalent is massive. 1.5 metric tons is about the equivalent of a very well instrumented golf cart. 20 to 40 metric tons is what you need to put humans on Mars. It is the equivalent of a small, fully furnished ranch house with a car in the carport. The other improvements that we've made and the other benefit that HIAD brings to the table is access to planetary locations. Specifically with the large aeroshells, we're able to increase planetary access in order to reach higher elevations. If you see the images on the right-hand side, the top right image shows the rigid aeroshells are currently limited to the areas in or altitudes with blue. Those are considered the northern lowlands of Mars. With the HIAD technology at 18 to 20 meter scale, we're looking to be able to reach 70 to 80% of the Martian surface, not including some of the mountaintops. Let's go to the next slide. So LOFTID objectives. So LOFTID is a demonstration. It's an orbital entry demonstration and test of HIAD reentry vehicle, specifically for NASA's heavy down mass missions, and we'll apply that to commercial applications as well. We will launch out of Vandenberg as a secondary payload on an Atlas V launch vehicle. John Donato is going to go through some of the details of that shortly. And we will demonstrate the HIAD technology at a scale, 6-meter scale, and entry conditions that are relevant for Earth and Mars mission and fusion opportunities. Next slide, please. Finally, I want to thank ULA. frankly, the NASA and ULA partnership has been outstanding. What ULA is bringing to the table are launch integration services. They brought to the table some adapter hardware for us, as well as our inflation system hardware. In addition, they're also contributing the parachute and mortar systems and the hardware recovery ship so that we can recover the LOFTID reentry vehicle and the ejectable data module that will have the LOFTID reentry data on it. In addition, NASA is contributing project management, safety and mission assurance, technical excellence, as well as the LOFTID reentry vehicle and ground systems. At this point, I'm going to hand it over to John Donano, who's going to walk through some of the more technical details of the LOFTID mission.
Thanks, Joe. So yep, as mentioned, we have John Donano up next, LOFTID's Chief Engineer. Go ahead, John.
Hello, thank you, Sarah. So I'd like to get you familiar with the LOFTID reentry vehicle itself. What you see before you is the stowed configuration as it would be nose up for launch. And the light colored area in the background shows the deployed aeroshell superimposed in the configuration it would be in reentry. So you can see the RV is 89 inches tall and 52 inches in diameter. And the entire aeroshell packs within the 1.5 feet at the forward edge of the nose. And when it's deployed, it unfurls so that the entire RV for reentry is about 6 feet, 71 inches tall. The internals include the inflation system, and I'm pointing to the inflation system tanks in this slide. We have 2 tanks. Those were supplied, thankfully, from ULA, from their flight hardware. We have an ejectable data recorder on the lower left. That system allows us to capture all of the data and eject it from the vehicle as a backup in case we cannot recover the vehicle itself. So it gives us extra assurance that we will retrieve the fully recorded data. We also have a data recorder that stays on board to be recovered with the vehicle. And we also, to aid in recovery, and this was supplied by ULA as well, is the parachute system, which includes a pilot chute mortar that deploys and it extracts the main parachute, which is the large area that's packed in that section. So we divide the RV into segments, and the forward segment includes the inflation system and the structural interface for the aeroshell and the aeroshell itself. The mid segment houses the avionics, which includes the system battery and the control features of the vehicle. And the aft segment is basically recovery hardware, and it includes 6 camera pods that give us both video data and infrared imaging of the aft side of the aeroshell as it re-enters. Next slide. And now I'll go through the timeline and the ConOps for the mission, the concept of operations for the mission. As you can see, climbing from the left where we launched from Vandenberg, the primary mission, which is carrying JPSS-2 to orbit, it is basically completed in the first 30 minutes of the mission. The JPSS-2 satellite is put into its polar orbit, and the Centaur, the second stage or the upper stage of the launch vehicle, performs a contamination and collision avoidance maneuver. Then it does a transfer orbit to a lower orbit that's not in the same orbit as JPSS-2, and then it deorbits from that lower orbit to ensure that LOFTID is on a trajectory for entry. This entire time, LOFTID is powered off. This is part of our assurance to do no harm to the primary mission. We are grateful as a secondary payload to get this ride share with JPSS-2, and we want to ensure that LOFTID does not do anything to harm that primary mission. So LOFTID is very passive and stowed in an enclosed payload adapter underneath JPSS-2, and is completely powered off until after the deorbit burn is complete. Once the deorbit burn is complete, then the Centaur sends a command that powers on the lofted reentry vehicle. And at that point, the Centaur will jettison the portion of the payload adapter that is covering the vehicle. This exposes our stowed aeroshell so that it can be deployed. The lofted reentry vehicle sends the start inflation command to the aeroshell, and slowly it inflates until it's at its full pressure for reentry. After the aeroshell is inflated, the Centaur spins up the vehicle. And by spin up, it's actually a fairly slow rotational speed. It's 3 RPM, but it's enough to provide spin stabilization for reentry. And once it's pointed on its exact path for reentry that we've targeted for the environments that we want to see on the aeroshell, the Centaur then releases the spinning RV and it goes through a ballistic reentry. The Centaur diverts to make sure it's off the path of the RV, and the reentry vehicle goes through hypersonic, supersonic, transonic, and down to subsonic speeds. After it reaches Mach 0.7, we consider that the end of the experiment. After that, the data recorder is ejected. And after the data recorder is ejected, then the chutes are deployed. That gives it a gentle splashdown in the ocean where we hope to recover the vehicle and the data recorder. So for recovery, this occurs off the east coast of Hawaii. And this graphic gives you an illustration of where relative to Hawaii we'll be recovering, and an example of the vessel that we will be using from the University of Hawaii. This recovery effort is part of the Space Act agreement that ULA is providing, and will help get both the reentry vehicle, which we cannot guarantee will float indefinitely, but we expect it to be floating shortly after the mission, and it will retrieve the reentry vehicle and then retrieve the data recorder. One thing I did not mention during the ConOps was that we will also be transmitting data in real time from the vehicle. It is a limited data package that we get sent through the Iridium satellite system, and we receive it as an email, and this provides us minimum data. So even if we do not recover any of the assets that re-entered, we should be able to reconstruct the trajectory from the data we receive.
And so the whole focus in this effort has been to develop a path that can support not just us, but LEO commercial applications, returning products from cislunar and that marketplace, as well as getting on to Mars and having the downmass to really enable humanity's expansion. So to that end, and with that in mind, we kind of left NASA's focus to be on the HIAD and that technology maturation for the flexible thermal protection system. And we kind of focused on those core things that we would do, both from a normal launch integration, as you saw in that earlier chart, but also those things that have application for our recovery and recovery of our engines. And so we were going after the parachutes and the barge, as well as the flight environments. We did some unique things to have the precision nav to be able to land where we need to for this mission to have the ship be able to recover. And so we kind of brought the best of both organizations together through the collaboration to deliver this technology demonstration mission.
Basically, as far as heat flux, we're looking at about 40 watts per centimeter squared. And I have to admit, I don't remember what the heat load is off the top of my head, but we are looking to decelerate from 8 kilometers per second, or about Mach, I think it's Mach 25 times the speed of sound, down to subsonic. So Mach 0.7 is about where we say that the mission profile has ended, and that's when we're popping parachutes, the parachute system. So, all right, so the HIAD technology is basically a set of inflatable torus in a stacked configuration, and then over the front of that we have a flexible thermal protection system. It's 2 key parts: the inflatable torus structure. The inflatable torus provides the structure for the aeroshell. When people think of those tourists, they tend to think of those inner tubes you float around on a lazy river with. That's not what these are. These are closer and likely and they're closer in kind to the wheels on your car. They're very, very rigid. And then the flexible thermal protection system is a series of material layups specifically designed to withstand the aero heating and loads for this particular reentry. And we can tailor that to different atmospheres, different environments, different thicknesses. So for this particular mission, we understood what the entry was going to look like, so we've tailored it specifically for this entry. Think of it like a firefighter with a fire jacket going into a fire. There are specific applications that we have looked at for this technology, namely smart reuse being one of them for lower cost access to space. The other one is being able to put large payloads onto the surface of Mars. We've done a number of trade studies, almost a dozen at this point, over the last 10 to 12 years, looking at various technologies, down mass capabilities, and technologies. And what has come through is that LOFTID provides the largest mass, the largest opportunity for higher elevations, and given if you had to choose between a HIAD or say retro propulsion or rocket-based systems, you get a savings of somewhere on the order of $1.8 to $2 billion using a HIAD over retro propulsion, just in mass savings, what you have to send to a planet. No, I don't see this being used to drop Amazon packages into your backyard, but we have had some interest in space tourism, being able to utilize these the HIAD technology for escape capsules, as well as for retiring ISS key components that are too large to bring down currently with our current technology. Given that shuttle has been retired, we don't have a heavy down mass capability at this time, so HIAD is one of the key options for helping to bring back some of those really large payloads from ISS. So we have very specific level 1 requirements that we're trying to meet. Number one, we want to know that the vehicle has been set up properly for entry. It's on the correct flight path angle. And as John mentioned, we do have a little bit of data coming in real time, as well as being a full data set being recorded on board and on our ejectable data recorder. What we're going to be looking for is that the vehicle was set up properly, that the data shows that it's oriented properly, and then in the initial data bursts that come back through our satellite system, we're going to want to show post-entry that it is still oriented properly, and that we have we've slowed down, that our position, velocity, and orientation are correct and within the bounds of what we expect to see for this demonstration. We plan to have real-time data coming in, but it'll be data bursts. On the ship, we've got a TRAT system. It's an IR-based system that will be looking up. We will have real-time communication with our ship, who will be doing the active recovery. And the hope is that we should be able to give some preliminary feedback on the day, within at least a couple of hours of re-entry, saying that yes, we believe, based on the data we have, that it was successful or not. Anything more than that would be speculation at this time.
We do have a camera that the Centaur uses, looking forward to release payloads. It will be up looking at the aeroshell when it's inflated. It'll only be a small pie wedge of it because of the field of view. And then we also have cameras on board the vehicle. It won't be a live feed. The data is too heavy to transmit in real time on this mission, so it will be something that they provide to us after it's been downloaded to a ground station. before the Centaur re-enters. In terms of the heat load, that's a energy per unit area. So we use, in this case, kilojoules per centimeter squared. The max temperature we're going to see is somewhere on the order of 2,600 degrees Fahrenheit. But it's the aeroshell is going through multiple environments at once. It's not just heating, it's the loading. So we expect to see over 9 Gs in deceleration, and that inflatable structure is inflated strong enough to be very stiff against that load. We use nitrogen to inflate the structure. And I think I do have one go back. I think I misspoke when I said 18 times. It's actually 180 times the heat load that we saw on RV3. I was only off by a factor of 10 then. Did I answer your questions?
And the inflation pressure, the pressure once the HIAD's fully inflated?
We're taking it to 19 PSI.